with a new prop. So far we've had cards, we've had dice, and now we have this yellow thing. Does anybody know what this yellow thing is? Put your hand up if you recognize this. Yeah, okay, great. This is a game called Bananagrams, and it's a little bit like Scrabble in that you make words. So let me put up the Bananagram. So here are some of the tiles that we have in this thing. And in this game, you will be given these tiles, and you have to arrange them and put them in order to make a word. Silt, that's a word. That's great. And the question that we're doing today is, if you did it randomly, so if you had these 4 tiles, and you shook them up, and then you put them down sort of in a random order, what is the chance that you make a real word? And I have istla, which is not a real word. But fortunately for you, I did my homework, and I looked up online what are the 5 words you can make with these are silt, tills, slit, list, and lits. Those are all the 5 valid words, according to the Scrabble dictionary, that you can make with these tiles. And I want you to use that information to figure out what is the probability that when you shake them up and put them down in a random order, you get a real word. And I have it set up so it's a fraction. The top of the fraction is something, the bottom of the fraction is something. You're going to have to figure out both of those things. Once again, as always, in a sort of traditional class, we would probably just tell you how to do it. We'd say, this is the problem, here's the answer. I want you guys to try it first, so you get a feel for why is it difficult, and maybe you've seen how to do it in high school or something. So that'll be interesting. Any questions or comments before I set you free? All right, 2 minutes. Talk to your neighbors if you want to. How would you calculate these 2 things? And the top and the bottom both represent different facets of the problem. Okay. All right, there's about 20 seconds left. Who thinks they can be productive with more time? A few people. Let me add 30 more seconds for the few people here. Okay, time is up. Make sure you get your guesses in. Yeah, apparently you can do does not exist as an answer. So if you ever don't know the answer, you can do does not exist, and that will tell me that you don't know. Let's see what people said though. And the top box actually should be quite easy. So I'm expecting a lot of people to get the top box right. The bottom is actually the hard part in this problem. Let's see what people said for the top box. For the top box, out of 67 people, 61 people said 5, and that is perfectly correct. So there are 5 valid words. There are 5 valid words, and so the probability of having a valid word is going to be the number of ways you can have a valid word, which is 5. So it's going to be 5. And then the hard part is actually, what do you divide it by? So how many different words are there? How likely is each individual word? That's the hard part to figure out in this problem. And that's going to lead us to a nice idea. This kind of thing is sometimes called combinatorics or counting, because we're counting the number of total possible 4-letter combinations of these 4 tiles. Let's see what you guys said. Maybe you know the answer already. Okay, so a little bit. Some people are in 16. Some people are in 24. Is anybody in 12? Oh, look at this. Beautiful. We have all these nice powers of 2 coming out. So 256. If you've ever wondered why when you play StarCraft you can only have 256 units, it's because it's the power of 2. Same with 1024, and so on. So 64. So it's got something to do with these combinatorial type numbers of powers of 2 or something like that. 24 seems quite popular. And indeed, 24 is the right answer. So if you got 24, maybe you know what's going on. We're going to go over it carefully to make sure we don't mix it up with other ideas. But it is 24. Let's see why. OK, so I have a few different ways to show why. And I think I'm going to show you all of them so that you can think about it in more than one way, and whichever way works for you the best. Let's do a brand new note for this one. OK, so we want to show the probability of valid 4-letter word from L, I, S, T is 5 divided by 24. 5 is the number of words we can make. Maybe the number of valid words we can make. And 24, this is the hard part that we're going to have to count. This is the total number of words. The total number of possible, let's say, 4-letter combinations. Let's not call them words. 4-letter combinations. Maybe I should also avoid the word combinations. 4-letter sequences, 4-letter groups. I just mean any 4 combination of these letters in any order, even if it's not a real word. And there's going to be 24 of them. And OK, here is method 1. Here is method 1. And this is to show you the flexibility of what we showed you already, which is the tree method. Just use probability trees. Just use probability trees. OK, and what I'm going to show is for any individual word, the chance of getting exactly that word is 1 out of 24. So this is the claim for an individual word. The probability of that word exactly. Let's say, for example, e.g., let's do the word list. What is the probability we get the word list? So list, the probability that you get exactly the word list is 1 out of 24. 1 out of 24. And if you know this claim, that the probability of any individual word is 1 out of 24, then the fact that the probability of any valid word is 5 out of 24 will follow by the union. So let me do that as a little remark here before I go any further. Remark, the probability of a valid word equals, it's the probability of the 5 words added together. So you either get list, or I don't remember what the other ones were. Let's plus the probability of stilt, plus dot, 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 plus, there were 5 of them. What was the other one? The weirdest one was lits, which some people will disagree is a word, but is in the Scrabble dictionary. So there's 5 words. They are disjoint. It is not possible for it to be list and lits at the same time, and therefore you can add the probabilities. And so if the probability of each one is 1 out of 24, the total probability will be 1 plus 1 plus 1 plus 1, all out of 24, which is 5 out of 24. So once we prove that the probability of any individual word is 1 out of 24, then we're happy and we're done. Why is the probability of any individual word 1 out of 24? So here's the proof of the claim. We're going to draw a probability tree. And so I'm going to imagine trying to get list. And I'm just going to do it step by step. And you're going to see that the chance is 1 out of 24 by the probability multiplication rule. And for us to get the word list. So I got to shake this up. What has to happen in the first one? So I'm going to take one of these things and put it down. So let's see. I have not revealed it yet. But if I'm going to get the word list, this letter, the first letter in the word, better be the letter L. Ah, we got it. What were the chances of getting it right on the first round? It was 1 out of 4. So we draw a tree. Maybe I can put this back for the people on the left side of the room. Draw a tree for getting the letters right. Okay. And the first round, either we got it right or we got it wrong. We either got the right thing or we got the wrong thing. And I think there's only a 1 out of 4 chance of getting it right, and there's a 3 out of 4 chance of getting it wrong. And that's because we need exactly an L to come up, and there's only one letter that works. So if we want to get exactly the word list, then it better be an L first, and there's only a 1 out of 4 chance of getting it right. Once we get it wrong, we're done. So like we can never escape. So maybe this is the start of my probability tree. What about the second letter? The second letter. So again, either on the second letter, I'm going to get it right or wrong. And we can see what happens here. So I'm going to shake, shake, shake. We need to get the word list. I shake up my 3 remaining tiles, and I put one down, and then I ask, am I going to get it right or wrong? Well, let's flip it over. Bah! Oh, we got it wrong. In fact, there's only one tile that works. It has to be exactly the I. So the chance of it working is only 1 out of 3. 1 out of 3 for the second thing. And then the next one, you get it wrong with chance 2 out of 3. And finally, for the next letter, there's 2. If I had gotten it right, we could keep going. There's 2 tiles left, so there's a 1/2 chance of getting it right. And a 1/2 chance of getting it wrong. And last but not least, if you've gotten it right up until now, there's only 1 tile left, so you will get that one correct. So in other words, to get perfectly the word list, you need 4 things to happen in a row. First, you need to get the first letter right. Then you need to get the next letter right. Then the next letter, and then the next letter. And we can calculate the chances of each one, and we can combine these with the probability multiplication rule. So by the probability multiplication rule, probability multiplication rule, the probability of getting list exactly is 1 out of 4 times 1 out of 3 times 1 out of 2 times 1 out of 1, also known as 1 out of 4 times 3 times 2 times 1, which is 1 out of 24. So that is one way to do it, and that everything we've done so far has been already done in the course. In fact, I think you have a homework problem that is a little bit like this one. There's a light bulb inspector who is checking to see if the light bulbs are broken or not. Maybe some people have done that problem already. But so far, it's just a probability tree problem. And in fact, everything we're doing, you can always do with probability trees. It's just that sometimes it's more convenient to think about this a slightly different way, which we'll do next. But this is a good place to pause. Any questions or comments about the probability tree or what these things represent? All right, method 2.
Oh,
Oh, there's a question over here. Yes.
Prof. Nika, could you have drawn a bushier tree?
Yeah, that's method 2. That's great. Yeah. So method 1 is the nice thin the thin probability tree. Why is it a thin probability tree? Look, it's only kind of width 2. It's a right or wrong, right or wrong, right or wrong. Like it never goes crazy. And the different branches have different weights. So getting it right is 1 out of 4, and getting it wrong is 3 out of 4. But I could have been less clever and just drawn a big bushy tree, and that is method 2. Method 2 is the bushy tree method. Method 2, the bushy tree. And actually, the bushy tree is the same thinking and the same logically thinking about the same way. It's just sort of expanding things out. You'll see what I mean in a second. And in the bushy tree method, what I'm going to do is instead of calculating the probability of each individual thing, I'm going to draw a big tree that includes all the possible words. So I'm not going to do each one individually. I'm going to do a big tree for all possible words. Let me say words means sequences of length 4. Let me I'll tell you this: when you're writing a combinatorics paper, words just means any sequence. So math people think any sequence of letters is a word, but in this problem, we're talking about actual words. So I'm going to try to avoid using the word words for that. All possible four-letter sequences. Four-letter sequences. And on this big bushy tree, we'll be able to identify the 5 things. So we kind of, instead of doing it one by one and having to do this special little tree for each one, and then having this extra step from the remark of adding them up, we're going to be able to do that all at once. That's the nice thing about the bushy tree. And this idea of looking at all the possible 4-letter sequences and counting them up is a very common idea that will save us a lot of work. So by sort of knowing method 2, you can fast forward some problems that would otherwise be annoying. So here it is. Here's the tree. Instead of saying right or wrong, I'm just going to say, what letter did you get? And there's 4 possible letters. You could, at first, it could be L, I, S, or T. So instead of saying you got it right or you got it wrong, I'm just saying what was the actual first letter you got? It was either L, I, S, or T. And based on what happened, there's 3 possibilities for each one. So if you drew an L the first round, then the remaining letters are I, S, and T. And if you drew an I the first round, the remaining letters are L, S, and T. And if you drew an S the first round, the remaining letters are I, L, I, and T. Okay. I should have maybe picked letters that look a little bit less similar. But that's the world we're in. Okay. L, I, T. And if you picked a T, then the remaining letters are L, I, and S. And you can see why this is called the bushy tree, is already this tree is getting very large and very out of control. It's going to get even more out of control in one second. But you can count how many branches are on this tree so far by multiplying. So you see there were 4 branches in the first one and 3 branches in the next level. So 4 branches in the first level times 3 branches in the next level. So far there's 12 branches. Each of the 4 things has 3 things coming off of it. And there's about to be another 2 branches coming off of each one because there's 2 choices for the next letter. There could be S or T. It could be I or L over here, and so on. I'm going to stop doing the labels. You're going to have to imagine the labels in your head because I am lazy. Okay, here we go. So we got a really bushy tree over here. The point being that there are 2 options for the next letter, whatever letters were not taken on those 2. And finally, there's only 1 option for the 4th letter. So that's nice at least. There's only 1 option for the 4th letter. So we have this really nice bushy tree, and we know exactly how many things are in it. Okay. Wow, this is a really bushy tree. How many things are in it? 4 times 3, 4 for the first layer, 3 for the next layer, 2, and then 1. And because they are branching out like this, you can multiply them all together to see that there are 24 total branches, and every single branch represents a word. In fact, that very top branch, right? Let's look at this little branch on the top. Let's make this nice and thick. That is, we chose the L first, then the I, then the S, then the T. Let's write down the T over here. T. That branch corresponds to choosing list. And so why was the probability of list? Why was it 1 out of 24? Well, there's 24 total branches, and list is exactly one of them. Why are all the branches equally likely? Well, they're equally likely at every single step. It always sort of splits equally, and so all the branches must be equally likely. You could also do the 1/4, 1/3, 1/2 times 1 rule, and also see that each one is probability 1 out of 24. So maybe this is a remark. All branches are equally likely. Branches? That's not how you spell branches. Branch. Now I'm scared. Okay, let's rewind. Oh no. Branches are equally likely. So there's 24 of them, and so they're each chance 1 out of 24. Okay. So what have we done so far? So far we've sort of redone the argument from before, where I have this huge bushy tree, where before I had this very thin tree. But look, this thin tree sort of contained 3 out of 4 chance contains everything else, right? So it's sort of, the thin tree is grouping together the big tree, but grouping together everything except for a single path. So if you want just the word list, then everything else has a 3 out of 4 chance over here. Everything else has a 2 out of 3 chance over here, and everything else has a 1/2 chance over here. So the bushy tree and the thin tree both represent the same idea in different ways. Why is the bushy tree better then? Well, the bushy tree is better because the thin tree works for one word at a time, but the bushy tree, I can put all my words on here. So that was list. Let's find another word to highlight in my big bushy tree. List. What was another one? Another word I like is tills. So here's T and then I. So tills is this word. T-I-L-S. So this would be the word tills coming out over here. Tills. And in fact, we know there are exactly 5 words that work. So I don't even need to highlight them. I can just think about them in my head. There's 5 different words. There's 5 different branches that are actual words. Some of them, start by overlapping, but it doesn't matter. At the end of the day, there's 5 that work. 5 that work. That work. That was given in the problem. And there's 24 total. That was the thing we said down here. So therefore, the probability of getting a valid word, the probability of valid word is the number that work divided by the total, which is 5 out of 24. So the key kind of insight is that once you've drawn this tree and you know that there's 24 of them by this 4 times 3 times 2 times 1 argument, then you can do this 5 out of 24, and it's all very easy. In real life, you normally do this and don't draw the tree. So you just imagine the tree in your head. You're like, yes, the first layer will have 4. And then you write down 4 times 3 times 2 times 1 equals 24, and you skip all the hard work I did of drawing the big tree. But conceptually, it should be in your head. Why is it 4 times 3 times 2 times 1? It's not just some magic formula you memorize. It comes from this tree. Okay, this 4 times 3 times 2 times 1 idea has a special name. I will say the special name and the special incantation in 1 second, but this is a good place to pause. Are there any questions or comments about any of this? Okay, let me tell you the special name. 4 times 3 times 2 times 1, mathematicians, they call this 4. No, 4 exclamation point means 4 times 3 times 2 times 1. I don't know who came up with this idea of let's reuse the exclamation point to mean something other than excitement, but this is called 4 factorial. 4 factorial. And you'll see this very often. This is a definition for you. What does the exclamation mark mean? And this is the number of ways to put down a sequence of 4 letters. So create a 4-letter sequence with 4 tiles. And the order matters. I'll emphasize that over here. Order does matter. Right? So the word list and the word tills are 2 different words. In general, we would say n factorial, and that's n times n minus 1 all the way down to times 1. You start at the number n, and you work your way down, and it represents a big bushy tree splitting out with n things, then n minus 1 things, and so on. So this is a special math word, factorial, and it's going to come up more and more. Okay, how many people have seen the factorial before? Okay, amazing. Now it's going to get even more complicated. We're going to use the factorials to do some more stuff, and that is the next mathematized question. Can you figure out what happens if you don't draw all 4 letters? So here I have 5 tiles, P-O-S-T-R, and it turns out there are 7 2-letter words you can make. The 7 words are op, or, st, po, so, st, and tu. According to the Scrabble dictionary, these are all actual valid words. So even if you don't know what the word po means, maybe it stands for post office, P-O, I'm not sure. But here's the question. So there's 7 valid 2-letter words. But how many, we have 5 tiles. We're going to pick out just 2 to make a word. How many ways can we do it? Question over here, yeah. Why is ST there twice? Because I made a mistake. Is it 1, 2, 3? Yes, I wrote ST there twice. That's embarrassing. So you know what I'll bet you is happening? There probably are 7 words, because I looked it up online, and then I probably wrote down which 7 words there are incorrectly. So maybe for a bonus mark, can anyone figure out what is the word that I did twice while everyone is thinking of the math, if you can figure out what the missing 7th word is. But let's take it as a fact that there are 7 words, Don't worry about which 7 they are, and let's try to figure out what is the probability. You will end up with one of these 7 words if you do the same random game that we did before. Okay, once again, the numerator of this fraction should be very easy because it was sort of given in the problem, but the denominator is the hard part, and that's what we're trying to do. Okay, I'll give you guys 2 or 3 minutes to try this one out. All right, there's just over 15 seconds left to get your final guesses in. What do you think is going on here? Okay, let's see. How do you stop the timer? Okay. All right, so once again, the top should be easy. The top is 7. So there are 7 valid 2-letter words. The hard part is figuring out how many total ways things could come out. So once again, the hint says you can draw a big probability tree. And just like before, if you do it the sort of method 2 way, the probability tree will have 7 highlighted paths that work. Here, I highlighted 2 of them. There were actually 5. I got lazy, and I said, don't worry about where the other ones are. There's 5 of them. In this question, there are definitely 7 valid paths because there are 7 words you can make. So the hard part is what is on the bottom. So let's see on the bottom how many total different things are there. All right, so some people said 20. Did anybody say 120? Only a few people said 120. 120 would be 5 factorial. 5 times 4 times 3 times 2 times 1. But the correct answer is indeed 20. So if you said 20, that's very good. And the way to do it is, again, just this probability tree. So you could set it up the narrow probability tree, and you could have 2 levels, where the first level is 1 out of 5 and the second level is 1 out of 4. Or you could imagine a probability tree that looks like this, with only 2 levels deep. So this is 2-letter words, 2-letter words from 5-letter, say, bank. So you have 5 letters in your that we're shaking, and we're putting out 2 letters, and we're going to draw a tree with two layers. So we're going to have a 2-layer tree, a 2-layer tree. And again, if you draw the full tree, it'd be extremely, extremely bushy, and you're going to be sitting there forever. So sort of, I'm going to draw it like this. I'm going to do a dot, dot, dot. So dot, dot, dot does a lot of heavy lifting in math. That means just continue the pattern in the way I'm thinking of. And so there are many different ways the first letter could come out. There's 5 ways this one could come out. And then for each of those, there's again, ... 4 ways for each. So times 4 ways for each. And so, for example, it could be T and then O or whatever, but there are 4 for each of them. So here, I do this, ... So this is the kind of cartoon you would draw on your page that looks, you know, if you don't know what you're doing, this looks like an insane little diagram. Like, what could this possibly mean? But hopefully, after having done this one in gory detail, this one makes sense to you in your head. And therefore, there are 20 total branches. So 20 total branches. And the 20 came from 5 times 4. 5 times 4. And how many of them are valid? 7 valid branches, because there are 7 valid words. So once again, you could imagine if you wanted highlighting the ones that are valid. Where's my highlighter? Here it is. So yeah, maybe this is one of them. And so therefore, the probability is 7 out of 20 because they are all equally likely. So therefore, the probability of a valid word is 7 out of 20. Okay, very nice. This thing also has a name. So this also has a name. So the new definition of this kind of thing, I call this the falling factorial. There's lots of different notations, but I write it like this. This is the falling factorial starting at 5. So it's 5 times 4, and you keep going down until you've reached 2 terms. So you start at 5, and you're going to do 2 multiplications with 2 terms, and you go down by 1 every time. In general, you could do n falling factorial k. You start at n, you go n minus 1 times ... and you're going to stop when you get to k terms. What would you be at if you're doing k terms? You would be at, not at n minus k, but n minus k plus 1. So that can be a bit confusing, but if you just think about it as the number of terms, it's okay. Some people call these with, they either call them with a P or a C, and I always get them mixed up. So let me double check my notes so I don't tell you something incorrect here. This one is the P. They say P52, where P stands for permutation. I can never remember which one's permutation and which one's combination. Falling factorial is very clear for me. This is the one in my math community. This is what they use. This you will never ever see in a math paper in my math community, but you will see it in other people's math community. So it's a good one to know. This stands for permutation. So for me, a permutation is something slightly different. That is always the full set of putting them all in order. Like the thing we did before was a permutation. This thing is a permutation to me. And this thing is not. But again, different people are different. The thing that you need to know is how it works in real life. So thinking of this tree and the falling factorial, you start with 5 things, and you go down 2 choices, so you get 5 times 4. Any questions or comments about that? Yeah. What is this? Yeah, so that's included. That's included in the multiplication. Is that? So for example, if k equals 2 and n equals 5, that's 5 choose 2, you would get 5 minus 2, which is 3, plus 1, which is 4. So that's the 4 that you multiply. So this says start at n and keep multiplying until you get to n minus k plus 1. And that's where you stop. That'll be the last thing. Yeah. OK. So the falling factorial, and this is used to count. This is the number of k letter sequences from a bank of n letters, right? And if n equals k, then you're back into the case we were in the original problem. If n is different than k, if k is less than n, then it's counting these short words. Maybe I should also specify the bank is of unique letters. They're all different. We'll have a case where they're repeated coming up soon, and then you have to be a little bit more clever. All right, any questions or comments about that one? Yeah, Professor Humphrey, what do you call this thing?
What I'm curious about is those 7 letters, the 7 valid 2-letter words. Could you put those up again?
Yes. So I just did this on, I will defer
and there's one missing.
Responsibility to the Scrabble dictionary. Yeah, there's one missing?
Well,
Well, I have
What
ST
kind of
down
a
here.
valid word is ST?
I think it's short for street. Yeah. Did you find what it was?
So it's an abbreviation. They count abbreviations?
I guess they count abbreviations. So someone is saying it could be OS. OS. I don't know. This is like when you watch the Scrabble World Championships, most of the words are not real words.
They're not real words. Okay,
so yes.
That's how they get.
I remember, I
OT
have a
and-
vivid memory of playing with Scrabble with somebody and they put down the word ZA, Z-A, and I challenged it, and Z-A is a word. It is short for pizza. You know, I'm going to go get some ZA. That's a good Scrabble word.
I guess that's why I don't play Scrabble.
That's why, yeah, I don't like Scrabble either for that reason. I like Scrabble with people who don't know all the two-letter words. Yes, okay. Was there another question or comment? Yeah, so I have ST twice, and I should have OS probably instead of one of the STs. All right, great point. Okay, so we've done taking the words. How many sequences can you make with all of them? How many sequences can you make with less than all of them? The next thing that is a really tricky issue is order versus not in order. So I'm going to pause this while I read it. To do this, instead of using the Scrabble tiles, because when you put down tiles, the order always matters. If you are writing a word down, the order of the letters always matters. But in card games, so I'm going to go back to the cards here. In card games, in some card games, the order matters, and in some card games, the order does not matter. So let me get what I'm saying here. I got king, queen, ace. Here's my ace. I just need the 10. Let me see if I can find the 10. Okay. So here are my cards. So I've got the 5 cards that I mentioned over here. 10, jack, queen, king, ace. And in some card games, the order matters, and in some card games, the order does not matter. So if it's in your hand, usually the order does not matter. You're allowed to move things around in your hand. If you have ace, king, queen in your hand, that's the same as having king, ace, queen. But if you deal out the cards in order, sometimes the order is very important. If an ace comes out first or a king comes out first, that is different. So the first thing I want you to do is, from these 5 cards, how many different 3 card combos where order matters, how many can you get? So ace, king, queen is different than king, ace, queen. They have the same cards, but in a different order, and that counts as completely different. And then I want you to do it where the order does not matter. So ace, king, queen is exactly the same as king, ace, queen. And that would be like putting it in your hand, or maybe all the 3 cards come out at once and the order doesn't matter. So you got to do it both ways. And you have to know how to do it both ways, and you have to know when is this one right and when is this one right. In this problem, it's telling you order matters versus order doesn't matter. Sometimes it's a little more subtle, but that's what you have to do. Are there any questions or comments about the question? All right, let me send you out into the world to count how many different ways there are to do these things, and we will take it up in 2 minutes. All right, there's 30 seconds left. to put in your guesses. One of these two is very straightforward, we just did, and the other one is a little bit tricky, so you have to think of it in the right way to sort of figure it out. But regardless, put in your guesses. If you don't know one of them, you can put a D and E in. A slash does not exist. Okay. Let's take a look at what people said. So the one that is like the one we just did is the one where the order matters. So if the order matters, it's just like the letters. That is exactly what we just did. That is this first one up here. So let's see if people figured that one out. Okay. If the order matters, let's see, 1 or 2 people, 48 people are in 60, and 60 is the right answer. So let's write this one down. So why is it 60? Well, again, you can think of the big tree. So getting more and more lazy with our trees. Here is our big tree. Big tree. And there are 5 choices in the first layer, and then each of them has 4 choices in the next layer. And then each of them has 3 choices in the next layer. So this is a cartoon of the tree, right? I haven't drawn the full tree. I've just drawn enough of it to remind me what's going on. The first layer, there's 5 choices for the first card. For each of those, there's 4, and then there's 3. 5 times 4 times 3 is 60. 60. Also, so this would, you could write this as 5 following factorial 3. That's the number of ways you can get the 3 cards in order. And the order matters because if you get it on the first branch or the last branch, that is different. So this is the big tree. So this is order. Order does matter. Order matters. Okay. The big question and the new thing, the hard thing, is what if the order does not matter? What if the order does not matter? And let's see what people said for that. So there were 60 ways where the order matters. If the order does not matter, then how many ways are there? And here we are a lot more split. So some people in 10, some people in 20. Some people don't know. That's great. Okay, you're going to learn something today. That's exciting. Okay. So how are we going to do order does not matter? And for order does not matter, here is the big idea. This is the idea to get the order does not matter, is group together hands, or maybe I'll say sequences where order matters. So group together the order matters. How many groups? So this is the big idea. So let me give you an example. Let's say we had ace, king, queen. And let's do it ace, king, queen. So if we do this and we say order does not matter, then there is only one hand with ace, king, queen. But if there is order matters, ace, king, queen can manifest itself in many different ways when order matters. So it could be king, queen, ace. It could be like this, where it's ace, king, queen. It could be like this, queen, ace, king. And so the idea is one unordered hand can become a group of many, many ordered hands. So one unordered, that corresponds, and I'll write a funny arrow like this, to many, many ordered. So this is just saying there's many ways you can rearrange this hand of cards. If you're going to deal them out one at a time, there are many ways you could do it. And so there are many branches on the tree that all correspond in this big tree, this big bushy tree where the ordered mattered. There are many different ways you can have ace, king, queen appearing. So maybe there's one over here. Maybe that's ace, king, queen. Maybe there's another one that is the same hand of cards where the last 2 cards are swapped. So the first one is the same, and then the next 2 are swapped, right? So this could be ace, king, queen, and that one could be ace, queen, king, right? Those are the same unordered thing, but there are many ways you can represent them as an ordered thing. That's the big idea. Once you know this idea, the thing you got to do is say, okay, many, how many? And in fact, this is the very first problem we did. How many different ways can we take this collection of 3 cards and put them in some order? If they're unordered, how can we put them in order? This is the very first problem we did with the 4 letters ISTL. Here there's 3 cards. That is the factorial. So not only is it many ordered, how many is exactly known. How many? How many? The answer is 3 factorial. 3 factorial, which is 3 times 2 times 1. There's 3 choices of these 3 cards. Which one I'm going to put first? 3 ways, then 2 ways for the next card, and then only 1 way for the last card. That is the very first problem we did. So if you remember that very first problem, then you have answered how many different ways there are. And that means on this big bushy tree, not only can we say there are many ways that correspond, there's exactly 6 ways. 6 ways. So 6 ways that correspond to one hand. So when we say 6 ordered ways that correspond to one unordered hand. So that's the big idea. Now if there's 60 total, and we can group 6 of them together to make one of these unordered hands, how many groups are there? Therefore, there must be so we started out with 60 total ways. Each group is size 6. How many ways are there? There must be 10. So this is the total ordered. This is the rate, or the group size. The group size. And this is equal to 10. That must be the number of groups. Number of groups. So there's 10 hands you can get where order does not matter, because there's actually 60 ordered ways, and they come in groups of size 6. The groups of size 6 was 3 times 2 times 1. That was the first problem we did. This thing, like the other things, is so important it has a name. This is the next definition. This is, you would write this like this. You would say 5 cards. We had our 5 cards over here, and we are choosing 3 of them to make an unordered group. So 5 choose 3, and in this case it is 10. This is the number of ways to get an unordered hand of 3 cards from a bank of 5. Okay. And what was the formula? Well, what we actually did is, in general, we started out with the number of ways you can do it in order, which was the falling factorial. So in general, this thing, you write, if you have an n card bank and you're choosing k of them, then you start out with the number of ordered ways to do it. That was the previous thing we did, and n falling factorial k. And then you have to divide by the number of ways you can rearrange those k cards. That's divided by k factorial. K factorial. If you were going to write this out, you could write it out like this: n times n minus 1 times dot 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 all the way up to n minus k plus 1, the thing we had before with k items, divided by k times k minus 1 times dot 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 times 1, also with k items, but starting at k. Sometimes people also do something very silly, is they write it like this. They write it as n factorial divided by n minus k factorial times k factorial. In other words, instead of starting at n and going all the way down to n minus k plus 1, they start at n and they go all the way down to 1, and then they add some stuff on the bottom to balance it out. Both of those are correct. In practice, you almost always use this formula, even though, I don't know, for whatever reason, this one is more popular in the literature. People like that one. But this is read out loud as n choose k, n choose k. And sometimes people write it like this. They write c and they do nk, c n k. And this one stands for combinations. I guess in some universe, combinations, the order does not matter, and permutations, the order does matter. However you want to think about it, as long as you have this idea of these 3 concepts: the factorial for doing the full thing, the falling factorial for a subset, and the choose for doing the order doesn't matter. All right, we have 1 minute left. Are there any questions or comments? All right, next class, we are going to do a doozy of a problem, which is to do this one. What happens if there are repeated letters? So next class, we're going to do the word pepper. So it's something divided by 6 factorial. Maybe I'll leave this open as a little bonus problem. If you think you can figure out what should be on top here, then please go ahead and do it. We'll do this one on Friday's class. And the repeated letters make things more complicated. Okay, see you on Friday.